today we shall start with the discussion on the different specifications of logic families by which you characterize them. Okay. So, we had already discussed a little bit last class. So, we shall now go into the details. So, the first one which we shall take up is propagation delay. So, what is the propagation delay of a logic circuit? Okay. Now, if you have an input, say if you take an inverter, say, okay, and the input waveform, if the input waveform is like this, okay, the output waveform is going to be something like this, all right. Okay. Now, the propagation, so this is how the input and output varies. The propagation delay is defined as the difference or in time between the 50% points of the input and output waveform. That is, if you take the this is the logic low and this is logic high. Okay. So, midway between these logic low and logic high, okay, the instant at which you have the voltage is at the middle point of the input waveform, and this is for the output waveform. So, this difference in time is the propagation delay for a high to low transition. Okay. So, we shall call it TPD HL. HL stands for high to low transition. Similarly, you can have a propagation delay for a low to high transition, okay, and these two propagation delays, that is for high to low transition and low to high transitions, need not be the same, they can be different. Okay. And usually the propagation delay of a logic circuit, okay, is defined as the average of these two propagation delays. So, the propagation delay will be the average of the high to low and the low to high propagation delays. All right. So, this is the definition of a propagation delay of a logic gate. Now, how do you measure it? Okay. Well, there is a very interesting circuit to measure this propagation delay, which is called the ring oscillator, okay, and that is used to measure the propagation delay of any logic gate. Okay. The ring oscillator consists of an odd number of inverters. Okay. So, if you have a NAND gate, for example, you can connect it as an inverter, okay, that is, you short the inputs, it behaves as an inverter. So, if you have an odd number of inverters, okay, say I will draw 3 inverters like this and you connect it like this, okay, this is called a ring oscillator. Okay. Now, what is going to happen is, suppose this is logic 1 here, okay, this is going to be 0 here, this is going to be 1 here, and this is going to be 0 here. So, this is connected here. So, this 1 becomes 0, and if this 1 becomes 0 here, this 0 is going to become 1, okay, and this 1 is going to become 0 and this 0 is going to become 1. So, at each output, okay, and again this 1 is going to be transmitted here. Okay. So, at each output the voltage constantly toggles between the two logic levels 0 1 1 to 0 like that. Okay. So, if you observe the waveform at any given point, okay, or at any input or any output of a logic gate, you will observe a waveform like this, okay, which is continuously varying. Okay. Okay. All right, a train of pulses. All right, and this train of pulses, okay, and the frequency of this waveform is going to tell us about the propagation delay, okay, because the time required for this 1 to change to 0 is the time required for this, once this changes from 1 to 0, this change has to propagate through all this and come back here, okay. So, 0, once it becomes 0, this has to go to 1, this 1 has to go to 0 and 0 has to go to 1, then only this changes, So, this the frequency, all right, that the time, okay, taken for it to change, okay, is determined by the propagation delay, all right. And since in each time period you have 2 transitions, okay, the propagation delay TPD will be given by 1 by 2 n f, all right, where f is the frequency of oscillation, or you can write it this way, actually f is equal to 1 by 2 n TPD, okay, that is f is the frequency of oscillation, okay, n is the number of inverters, okay, and 2 because in each time period you have 2 oscillations. Basically the time period of this, all right, is equal to twice n TPD, okay, the time period of this oscillation is twice n TPD, okay, the propagation delay, all right. So, this looking at the waveform and knowing the frequency, you can find out the propagation delay. In fact, this is a very important circuit and is used as a test structure whenever you are developing any logic circuit, okay. That is, you want to know that what is going to be the time period, or what is going to be the frequency at which you can operate this, or the delays, propagation delay of any logic circuit. You usually use this circuit, all right. Okay. In addition to the propagation delay, there are 2 other delay 2 other delays associated with the logic gate, what is called the rise time and the fall time, okay. So, the rise time is usually denoted by TR and the fall time by TF. So, TR is the rise time and TF is the fall time. So, okay, that is, if you look at this, observe this waveform, okay, here, all right, the time required for this to fall, okay, that is the fall time. Usually it is very difficult to find out exactly the time required for it to fall from the logic high to logic low, because at these points it takes, the transitions are very slow at the edges, okay. So, usually it is defined as in terms of the 90% and 10% points, okay. So, the rise time is the time required for the waveform to rise from 10% to 90% value, okay, and the fall time is from 90% to 10%, sorry, all right. So, these are the 2 other specifications which you may observe while if you look at a specification sheet of any logic family, all right. So, propagation delay, the rise time and the fall times, okay, and they are very important to know, okay, if you are going to make a circuit, all right. Okay. So, this is about the delays, okay. Then we move on to the next characteristic, all right, which is the power dissipation. So, the power dissipation is another characteristic, and it is a very important characteristic, especially in the present day scenario, where the trend is to pack in a large number of circuits in a given chip, as many devices as possible in a given chip. You have millions of transistors nowadays in the VLSI chips. Okay. Now, so if you are introducing so many devices, okay, the power dissipation is obviously going to go up. Okay. So, in order to be able to integrate a larger number of circuits, okay, larger number of components, okay, the power dissipation must be brought down somehow. Okay. In fact, some of the latest microprocessor chips, okay, consume as much as tens of watts of power. Okay. And if you consider that the voltages, okay, are power supply voltages, you know, is 5, it was 5 volts, now it has come down to 3 volts or so. That means a few amperes of currents, okay, okay, which is quite a large thing, you know, the small pins, they must be able to carry so much current, okay, and that is a big constraint. Okay. So, the power dissipation is a very important consideration nowadays, all right, and people are looking at ways to reduce the power dissipation. In fact, you must have one of the reasons, okay, there are many reasons for this, of course. One of the reasons why the power supply voltages have coming down, okay, is because of the necessity to reduce power dissipation. So, you know that you are nowadays you hear so much of low power circuits, okay, all right. So, a lot of research is going on in that area. Anyway, so this is a very important consideration, all right, power dissipation. How much power does a gate okay, dissipate? That is the basic unit, all right. How much does it dissipate, all right. Just so let us just take a circuit like this. Let us consider this circuit. There is a current source I, and there is a, so this is an inverter circuit, basically a BJT inverter circuit, okay, and this is driving a capacitive load. Okay. Now, there is a current source. So, if this transistor is on, okay, this current source, the current flows into the transistor, and this goes to saturation, all right, and the output voltage is low. And when the transistor is made to is cut off, okay, what happens? This transistor, the current cannot flow into the transistor, it goes into the capacitance and it charges the capacitance, the output voltage goes high, all right. In such a situation, if you look at the power dissipation, suppose we call this the PD, this is the power dissipation, okay. The power dissipation is given by VCC into I, all right. Then, now when you are charging this capacitance with a current I, all right, what is the delay, all right. That is, suppose the output voltage swing, okay, there is a term called the logic swing, okay, that is the change in the output voltage, that is the difference between the logic low and the logic high. Suppose it is given by VL logic, okay, all right. So, what is the delay when this capacitance is charged with a current source of value I, okay. You know that I, when you are charging a capacitor, I is equal to C dV dt, okay. So, if you write it, I is equal to C, okay. So, the change in voltage is VL, which is the logic swing, okay, and the delay will be given by, say, TD, all right, all right. So, now you can write this as, or TD is equal to C VL by I, all right. Then from these two expressions, the power dissipation and the delay, you can write PD into TD, okay, is equal to VCC C into VL, all right. So, this expression, so this PD into TD, it is an important figure of merit of a logic family, it is called the power delay product, all right, power delay product, okay. And you see that this is independent of the value of the current source, all right. Now, in a particular logic family, okay, you can suppose this is the basic inverter, okay. Now, you can change this value of current, all right, okay, by say for example, if you had a resistance, you can change the value of resistance, okay, all right. Now, that is going to affect both the power dissipation and the delay, okay, but the power delay product is independent of the current source, okay, value, current source value, and is just is dependent on VCC, that is the power supply voltage, of course here the capacitive load, the value of the capacitive load, and the logic swing, okay. So, this is a characteristic figure of merit for the circuit, okay. In a given circuit, you can operate it at different power dissipation levels and delay levels, okay, by changing the value of the current, okay. You have a circuit, if you just change the value of resistances for example, okay, in the circuit, okay, it will be operating at a different for example, if you increase the resistance values, okay, the power dissipation is going to reduce because the current is going to reduce, okay, but at the same time the delays are also going to be affected, okay, but so it is going to affect both the power dissipation and the delay, but the power delay product becomes independent of that, okay. So, this is a characteristic of the logic family, all right, and it does not, so you can operate it at different power dissipation or delay values. For example, you know, you may have come across some of these curves, you know, this PD versus TD, okay. Now, if you plot them on a log scale, okay, this both power dissipation and the delay, you will get these straight lines, okay, indicate constant power delay product lines, all right. So, that is here, you know, you can operate maybe a given circuit at this point or this point, okay, you can move along this line, that is in a constant power delay product by changing the value of this current source for example, okay. But of course, you must also remember that this takes into account only a capacitance which is a constant, but this is only true when we are operating the circuit. You just in the view of last class, you know, you must remember that only when the capacitances are the junction capacitance type, you know, for a BJT, all right. If you have the diffusion capacitance, this capacitance is no longer going to be a constant, but again it becomes a function of current, okay. So, when you are operating in the low current regime, okay, then only this is true. But anyway, so this gives us some idea, and if you can operate the circuit at any of these lines. In fact, if you see that, for example, an ECL would be maybe somewhere here, you know, or whereas a TTL, you know, would be somewhere here. That is, although you can operate along this line, you know, but in a TTL for example, there is a limitation, you cannot go below a particular delay, okay, because after that it is the other, it is no longer going to follow this curve, okay, because this capacitance, as we have seen in last class, the capacitance is no longer going to be a constant, you know, that is the other capacitances which take up. So, and for example, if you take I squared L, you know, it may be somewhere here, okay. Okay, I squared L has a much lower power delay product compared to TTL or ECL, all right. So, as a circuit this is a much better circuit, okay. But of course, there is limitations, as we shall see, that you cannot go to very low delays, okay. You cannot operate it at much very high speeds. So, anyway, we shall discuss that in detail. So, this power delay product is another important figure of merit or specific characteristic of a logic family, okay. What is the power delay product associated? Okay. Now, in fact, this power dissipation and the speed, delays go hand in hand, okay, and it gives rise to many interesting considerations. For example, if you look, let us take a particular logic family where the capacitance which we are looking at this here is, say, let us say, just we take some values, 50 femtofarad, say, VCC is 3 volts and VL is equal to 0.5 volts, all right. And then, so let us consider that many of these chips, the price consideration comes from the packaging, okay. That is, suppose you want a 1 watt package, okay, that is a package which can dissipate 1 watt of power, okay. So, that is the limitation there, that you must have the power dissipated must be 1 watt. Now, if you go for a 10 watt package, the price goes up, all right. So, maybe you want to limit within a particular package, all right. So, suppose you are going to this particular logic family, okay, suppose you are going to package it in a 1 watt package, okay, and suppose you want to have, say, there are, say, case 1, let us say, you want to operate it at a very high speed, that is the, say, very low delays of, say, 100 picoseconds, okay. Let the you want okay. So, you want to operate it the circuit at very high speeds. So, now the question is, for this high speed of operation, how many gates, all right, can be accommodated in a 1 watt package, all right. How do you do that? So, you have to calculate the power dissipation. So, you know that this expression here, okay, the product of the power dissipation and the delay is equal to VCC C into VL, all right. So, now what you can find out is, TD, all these things. So, you can find out the power dissipation per gate, okay, and so how many gates you can accommodate. So, I will just write it here. So, C VCC into VL TD. All right. If you put substitute all these values, okay, the what you will get is 0.75 milliwatt. So, the power dissipation is going to be 0.75 milliwatt per gate if you operate it at a delay of 100 picoseconds, all right. And so, now if you have a 1 watt package, so number of gates you can accommodate in the package is 1 watt divided by 0.75 milliwatt, that is 1300 gates in that 1 watt package, all right. Okay. Now, suppose in another case you want high packing density, all right, okay, the same circuit you want high packing density. Suppose you want 10 to the power 5 gates per package, all right, you have a more complex circuit, okay. So, what is going to be the power dissipation per gate? 1 watt divided by 10 to the power 5, okay. PD, power dissipation, is going to be 1 watt divided by 10 to the power 5, that is, okay, 0.01 milliwatt, okay. Okay. Now, if you write TD, okay, that is again you put down the values C, VCC, VL by PD which you got here, okay. you will find that the delays is going to be 7.5 nanoseconds per gate. Okay, you can just put down the values, you get this. So, which means that the delay is going to be much higher, all right. So, there is always a compromise, okay, between the power dissipation and the delay, all right. That is what I want to point out, okay, that they are, although you talk of power dissipation and delay as separate entities, but they are, there is a compromise always, okay. If you want to you can trade off between these two quantities, all right. So, all right. So, that is about the power dissipation and delay. Okay. Then we move on to the next topic, that is noise margin. Okay. That is the third one. All right, let us start here. The noise margin is also a very important characteristic of a logic family. Okay. And it tells you that how much noise the particular circuit can tolerate. Okay. If you are using in a noisy environment. Okay. Now, you have seen the characteristic of an inverter. We shall take up again the characteristic of an inverter. So, if this is the input voltage, this is the output voltage, it is something like this. All right. So, when the input is low, the output is high. When the input is high, the output is low. Okay. Now, so and this is known as the logic swing. Okay. The output high and the output low, the difference in these values is known as the logic swing. Okay. Okay. This difference is the logic swing VL, okay, which we have already discussed. All right. Of course, it is okay, and this is also an important parameter. Now, if a logic swing is high, okay, it is true that the noise margin is also going to be high. Okay, we shall come to the definition of noise margin, but anyway, if the logic swing is high, the noise margin is going to be high, but at the same time you can see that the delay also increases, all right, in a logic circuit, because the output of a gate has to has to change from the logic low to logic high. Basically, you have to charge a capacitor, and if you are charging a capacitor through a larger voltage, it obviously is going to take more time. Okay, if you are the voltage through which it is charging is less, it takes less time. So, the important thing is that all these characteristics, you know, are not independent, but they are sort of dependent on one another. Okay, all right. Now suppose you have a circuit like this. You have two inverters. Okay, we call this inverter 1 and we call this inverter 2. Okay, and so here what you have is, you can write V in 1 is equal to V output 2, and V in 2 is equal to V output 1. All right. Okay. Now, suppose this is the characteristic of inverter 1. Okay. So, I will just remove this. Okay. This is the characteristic of inverter 1. Okay. Now, let us call this V output 1, V output 1, and this is V in 1. All right. Now, this is equal to V output 2, and this is equal to V in 1, V in 2. All right. Now, so if you want to now plot the input output characteristics of the second inverter, that is inverter 2, this is the output axis, this is the input axis. Okay. All right. So, you can plot it like this. Okay. This is the same characteristics, they are identical inverters, you are just plotting it like this now, because this is the output axis, this is the input axis going this way. All right. And so, this now for this, in these two inverters, if they are connected like this, the points, the stable points of operation are the points of intersection of these two characteristics. Okay. So, you see that these characteristics intersect at this point as well as this point. Okay. So, all right, only at these points V input 1 is equal to V output 2. All right. So, but this point is actually very unstable because of the very high gain associated with any point, because if you have it at this point, any small perturbation, somehow noise or anything, it will move it away from that point. Okay. So, usually either the device operates at this point or this point. Okay. So, if this point, okay, is actually called this value V output low, okay, and this is V output high. All right. Okay. So, these are the two operating points, okay, this point and this point. Okay. These are the two possible operating points of the inverter. Okay. Now, where does noise come in now? Suppose you have a noise source introduced here in between. Okay. Let us call this Vn. Okay. Now, what is happening is, suppose this is low, okay, this is VOL say, okay, and so you have the same input to this. Okay. Now, when the input here is VOL, the output is high. All right. Now, if the input here it is VOL, okay, here it VOL. So, here the input to gate 2 is VOL plus Vn. Okay. And so, what is going to happen is the input point to the inverter 2, okay, actually I should be in this way, okay, all right, anyway does not matter, it is the same, actually it is whichever way you look at it, all right. I actually should have drawn the noise source here anyway. So, as this noise value increases, what you are doing is you are shifting this operating point, all right. So, it is moving like this. So, even if the noise source is this much noise voltage, okay, the output voltage is still equal to this high, this is VOH, this is also VOH, this is also VOL, okay, this is also VOL, this is also VOH, okay, all right. If you look at this way it is the same, all right. Now, so when the input voltage changes, it is still VOH, almost close to VOH, but if this input voltage changes by a lot, okay, then the output voltage may start to fall, okay, and then only it creates problems. Okay. Now, what is the input voltage up to which it can tolerate? Usually the definition is that where the slope of this curve becomes equal to -1, okay, that is the maximum you can tolerate. Okay. All right. Okay. When the slope becomes -1 at this point, okay, this is called VIL, okay, that is the maximum value of the input voltage which is going to be considered as a logic low by this circuit, that is VIL, the maximum value of the input voltage which is considered as logic low, that is VIL. Okay. Beyond that it is no longer logic low at the input. Okay. Similarly, at this end you have another minus slope is equal to minus 1 point, and this is called VIH, okay, which is the minimum value at the input which is considered as a logic high. Okay. So this is logic high at the input, isn't it? All right. Normally if you apply this voltage, it is logic high, but if the noise source pulls it down, you know, up to this point it is still considered logic high, after that it is no longer logic high. Okay. So it can tolerate this much amount of noise when the input is high. Okay. And and when the logic is low, it can tolerate this much amount of noise. Okay. So there are two noise margins, okay, usually one is for logic low and the other is for logic high. Okay. So you have noise margin low is equal to VIL minus VOL, and noise margin high is equal to VOH minus VIH. Okay. Noise margin low is VIL minus VOL, and noise margin high is VOH minus VIH. All right. So these are the two noise margins, okay, in the circuit. In fact, there are other definitions of noise margin also, a more stringent definition. Okay. I should just point it out that suppose, okay, you have in this circuit, if you go back to this circuit, you have another noise source here, okay, and these are equal and opposite noise sources in the sense that when this end is positive, you know, okay, if this goes positive, if this is increasing the input voltage here, it is pulling down the output voltage, okay, this noise source, and this noise source further pulls it down. All right, the equal and opposite, okay, and this is a more stringent condition. Okay, there are two noise sources and they are actually acting, both are acting in such a way as to change the state of the particular gate. All right. Okay, and you can this is, and for that particular condition, okay, when you have two noise sources, okay, the noise margin, all right, is actually given by the what is called this is called the maximum square noise margin. So sometimes you may come across this term, so you must know what it is. The maximum square noise margin, it is called the maximum square noise margin because the noise margin in this case is given by the maximum square that can be accommodated in this region. All right. That is, if you have the maximum size, in fact, I am sorry, this drawing is not perfectly correct. Okay, this the maximum square which you can accommodate here is going to be the same as the maximum square, okay, which you can accommodate here because they are sort of identical. All right, from my drawing it is not very clear. Okay, maybe I should redraw it. It should be it should go something like this. All right. So in fact, here the definition of the maximum square noise margin, you do not differentiate between logic low and logic high, it is the same. All right, because here in this case, if you look at this figure, okay, one of the transistors, one of the gates will be at logic input will be logic low, and the other gate the input will be logic high. Okay, and all right, so it does not matter. All right, so that is called the maximum square noise margin. All right, and is given by the maximum square and is given by the side of the maximum square which can be accommodated inside this. All right, so this one is going to be so this value here is called the maximum square VMS, okay, maximum square noise margin. okay, this side of this square. All right. So, this is another although generally people talk of low noise margin low and noise margin high, these two noise margins, okay, but this maximum square noise margin is also sometimes referred to, okay, and that is the definition of the maximum square noise margin, where you have two noise sources, okay, and sort of aiding each other, all right, helping each other, so that even a smaller noise can create more damage, all right. So, that is about noise margins, okay, and obviously the larger the noise margin, the better is the circuit, because it can operate at more noisy environment, okay. In fact, the reason why the digital circuits have become so important nowadays is actually, even you talk of audio circuits, even some things like analog, that is very much analog, like for example audio, okay, amplifiers, you have digital amplifiers, okay, and many other things, okay, which is, okay, everything becoming digital nowadays because of the larger noise immunity, you can say, of digital circuits, okay. Because if you look at this circuit, you can see that if you just go back to this, okay, see that even when the input changes from by a long margin, okay, the output remains the same, okay. So, even while you have a lot of noise, okay, it does not affect the output, because here the gain is almost 0, okay, isn't it? The gain is almost 0. So, the region where you operate a digital circuit, at this point or this point, okay, the gain at these points are very small, very low, almost 0, okay. So, if you have a noise that is almost wiped out, okay, there is no effect of noise, only when you come to this part, then it becomes important. So, that is why the digital circuit is much more immune to noise, okay, it does not easily get affected by noise, okay, you understand that. So, okay. So, this gives us the idea of the noise margin. So, what is the maximum noise the circuit can tolerate, okay. Obviously, if you want to have a higher noise margin, the input output characteristics should be more symmetric, okay, all right. We shall see that as we go about. That is, basically the noise margin low should be, it is no point having a very low a very high noise margin high and a very low noise margin low, because it is mostly governed by the lower value, okay, all right. So, if you have a symmetric input output characteristics, that is the transition point, I will just go back to that again, this one here, all right. So, this another definition I should say here, this point, if you look at this point also has a lot of significance, that is, it is called the logic threshold, all right. Logic threshold means that at that value, if at this point, okay, the input is equal to the output, all right. At this point, the input voltage is equal to the output voltage, all right, that is, it is like this, all right. Now, when the input is low, if you call this the logic threshold value here, okay, when the input is lower than the logic threshold, okay, the output is higher than the logic threshold, okay, and when the input is higher than the logic threshold, output is lower than the logic threshold. I just give you an example. I shall just draw two curves, two inverter characteristics. So, this is one inverter characteristic, all right. So, if you now, and this is another inverter characteristics, they are both inverter characteristics, okay. Now, if you draw this, okay, the logic threshold is here for this one, okay, all right. So, this is slope is equal to 1. So, V in is equal to V out on this curve, okay, and if V in is slightly less than this value, okay, then V output is higher than V in because it is inverter. And so this is the logic threshold. Okay, this logic threshold is much lower here, this logic threshold is much higher there. Okay. Now obviously if you are operating from 5 volts and this is 5 volts, all right, if the logic threshold here is 2.5 volts, okay, this is a more symmetric inverter characteristics, all right, this may be 1 volt say, okay, all right. Now if for this one, okay, if I draw the curve like this, as we had drawn previously while drawing the noise margin, okay, all right, you will find that the noise margin low is very small, whereas the noise margin high is very large. Okay. But again, it is the lower value which is important. Okay. It is no point having a very high value of noise margin high, okay, and having a very low value of noise margin low, because it is if you will have in a circuit always some gates at operating the output at logic low and some at logic high, and so if a small value of noise margin, a small noise is going to upset the operation, okay, if you have a low value of noise margin low. Okay. So it is always preferred, the ideal inverter characteristic would have the logic threshold somewhere midway between logic high and logic low. Okay. There you have, you see in this case the noise margin high is this much, okay, noise margin low is this much. Okay. So it is almost, they are almost same. Okay. All right. So the ideal characteristics would have the logic threshold somewhere. So logic threshold at half, we can say ideally logic threshold should be half VOH plus VOL. Okay. That would give you more or less a symmetric noise margin. Okay. That is the logic swing, okay, whatever logic swing is there, it is properly utilized. Okay. All right, to have almost equal noise margin low and noise margin high. Okay. So this is also very important from the point of view of characteristics. Okay. Finally, the last point, the last characteristic which we have already pointed out is the fan out. Okay. The fan out is of a logic gate is the number of outputs you can connect, okay, the from or the number of outputs or number of gates which it can drive basically. Suppose you have a NAND gate, okay, and you are connecting to large number of other gates. Okay. So this is the fan out, how many gates you are connecting to, all right, and this also there is a limit to it. Okay. So we shall take up that subsequently when we discuss the actual circuits. Okay. So this is also there is a limit, okay, the maximum limit for that. So that we shall next class we shall take up actual circuits, okay, start off with the actual logic circuits and see discuss in terms of these characteristics which we have studied today. Okay, thank you.